In this video, we're going to go over the theory behind Riemann sums and how you can use them to approximate the area under the curve. Let's get started. So let's start off with the problem that we're trying to solve here. Basically, we're trying to find the area under the curve of a certain function between two bounds where x equals a and x equals b. So for example, like in this case, x equals a would be 0 in this case, the lower bound, and then in this case, x would be 2, the upper bound, and that's the lower bound is a, the upper bound is b. And right now I'm just showing different functions here, and basically what the area under the curve between the bounds 0 and 2 would look like for each of them. Now the question, another questioner, I should say, is why are we trying to do that? That's a deeper question I'm not going to get into right now, but basically I'll just say that it turns out a lot of problems in calculus can actually be solved by finding the area under the curve of some function. So I'll just suffice it to say at this point, it's very useful to be able to do this in calculus. Now, in order to do this, we can actually figure it out for a lot of functions given what we already know. Let me just start there. There are some functions, specifically the simpler ones, that we can just use kind of our geometry knowledge to figure out. So like this function, if you recognize that this is really the quarter area, it's basically 1/4 of a circle of radius 4, or sorry, radius 2, I mean, then you can think about it. What would be, from geometry, the area of an entire circle, pi r squared. So in this case, pi 2 squared, so 4 pi. So if 4 pi is the area of the entire circle, then what's the area of 1/4 of the circle? Well, 1/4 of that. So just pi. So you can use that kind of logic. And here, what kind of logic would you use here? This is really, if you think about it, the function y equals 3. Hopefully that's clear, just a constant function. You can look at this as a rectangle of width to height 3, so area has to be 6. Pretty easy. Again, this is like a linear function. This is y equals x minus 1 is what this function is. And if we're trying to find the area under the curve, in this case, it's actually a little different. It's from 1 to 2 rather than 0 to 2. How would we do that? Well, you can look at this as a triangle with a base of 1 and a height also of 1. So what's a 1 by 1 triangle? If you plug it into the area for a triangle formula, 1/2 times 1 times 1, 1/2. So the area of that's 1/2. So you can figure out a lot of functions or the area under them between two bounds with using basically your geometry knowledge, if you can visualize it. However, when we get to something like this, that breaks down. We don't really learn, at least in a typical geometry class, you don't learn how to find, say, the area under a parabola, y equals x squared. So ideally, what we're looking for is some technique, and ideally a technique that works for all functions, no matter how complicated the shape, that allows us to figure out the area under the curve. That's what we're trying to do here. And Riemann sums are a very important piece of that, a critical piece of that, actually. So that's what we're trying to do. Now you might be wondering, why are they called Riemann sums? So the Riemann part is named after a famous mathematician in the 1800s named Bernard Riemann. He came up with the idea that we'll be talking about in this video, or at least he was the first one to describe it in scientific papers. So that's where the Riemann part comes from. This person's name was Bernard Riemann. And you might also wonder, where does the sum part come in? Basically, the idea, and we'll talk about this in a second, is that his idea, or a piece of his idea, was to, instead of trying to find the area under the entire function, which can get pretty difficult depending on what it is, instead break it up into smaller chunks of area and just try to figure out those and then add them all up at the end. So that's his idea. That's where the sum part comes in. And so because we're basically adding up a bunch of smaller areas to get one larger area. And we'll talk about this a little bit later. So you might be wondering, how do we actually do that? The first idea to actually do that is to break things apart according to partitions. And again, this is like part of the idea that Bernard Riemann came up with hundreds of years ago. So what is a partition? It basically just means subintervals. So that's another word for partition, is subintervals, specifically on the x axis. So if this is our x-axis, this would be like our entire width here of the shape. Then basically a subinterval or partition is basically a smaller piece of that. So like this would be the first partition. This would be the second partition, or the x values in the second partition. Third, fourth. You can basically chop things up vertically into separate slices. Is how you can think about it. And now, like we said before, if the problem is a little bit easier now, if you can figure out the area of each of these slices, or at least an approximation, we'll just deal with an approximation now because that's what we're trying to do. We're not trying to get it perfect yet. But if you can just figure out an approximate area for, say, this first partition, an approximate area for the second partition, approximate for the third, approximate for the fourth. If you can figure those out, which are a lot easier to do than the whole shape, then you can just add them all up. And that's the sum part of Riemann sums. So how do we do that? So how do we figure out the area of each individual partition? Basically, we can draw a shape that looks roughly like the area. That's the best idea. So one idea, and I don't know, maybe in this example, we'll draw like a rectangle. So we'll draw a rectangle like that, maybe. I'll draw it a little better. We draw like a rectangle, and it doesn't have to be perfect, but it does have to be pretty good. And then you draw like kind of a quarter of a circle. Again, that's not a very good circle, but maybe a quarter of a circle would be like that. So you can use other shapes that you already know how to draw. That would be like one option. Another, but that's a little bit complicated if you think about it, especially as you like involve more shapes. And also, it's not even that close. There's quite a bit of error actually. We're kind of overshooting what the true value under the curve is at that spot. So that's one idea. Another idea, maybe we can use like a trapezoid. A trapezoid. This is technically a trapezoid. There's actually another rule that we'll talk about later called the trapezoidal rule where we kind of do this. But this is one option. And that's actually pretty good. That's not bad, the trapezoidal rule. Another option is we could just do a rectangle. So if I just did a rectangle, that's, again, it's definitely worse than the trapezoid usually. Or almost always, I'll say, worse than the trapezoid. But it's also a lot simpler to think about too. So basically, these are all pretty good, I'll say. And in general, you always have a trade-off between something that's going to give you a more complicated equation, but is more accurate, like the things we tried first, versus something that is less complicated and easier to use, but also a little bit less accurate. That's like this rectangle here. So the rectangle is probably the simplest thing we can do, but it's also of the options we talked about, it's the least accurate, but it's still pretty good, and that's kind of the point. We're actually going to choose the rectangle, even though it's a little bit less accurate, because it's so much less complicated. And actually, there's another thing we'll talk about later, that the fact that the rectangle gives us a little bit more error actually doesn't matter in the long run, because we're going to talk about other techniques. There are very clever techniques we can do to eliminate that problem, but that's for later. So right now, just keep it simple, or as simple as we can, because it's already going to get pretty complicated. We're going to just use rectangles to approximate the area. So if we're trying to approximate the area under each curve with a rectangle, the next question is, which rectangle do you choose? Specifically, which height of the rectangle do we choose? So like if I come down here, so here's a piece of the rectangle, so that's definitely going to be a part of it, but do you make that the height of the rectangle? That would be like if we choose the height at the very left, or do you choose the height at the very right? Or do you choose a height somewhere in the middle? Like realistically, how should you choose? Like it looks like some are better than others, but how can you choose, or how do you know what to choose? The answer is that you have different choices. So the only thing that really matters is that you choose some y value, some height that's actually within that partition. So for example, you should not be choosing a height here for your rectangle, because there's no y value on the actual function there that is that height, right? There's no y value up there. But there are y values, like on this partition. In general, on any partition, there's always going to be a range of y values. But in general, I'll try to draw this. But as long as you pick a height in between here, you're going to be pretty close. As long as you pick an actual height on the curve, you're going to be pretty close. And it's actually a little bit less strict than you might be thinking. Technically, according to the integral, you can choose any one that you want. So what I'm going to do, it doesn't really matter what you choose. I'll just leave it at that. So hopefully that makes sense. So now think about what we have. Remember, we're trying to find the area under the curve between A and B. And what we've done is we've broken things apart into partitions, and we're trying to find the area of each of those. And to find the area of each of those partitions, we're just approximating it as a rectangle. And just to choose the height of the rectangle, the only real rule is that we just have to choose a y value that's actually on the function in that partition. And as long as we do that, we'll get pretty close, as you can see what we have right now. One other thing I want to emphasize is that you don't have to choose sample points the same way on each partition. So here on the first partition, you can see I chose the left bound. On the second one, I chose the right bound, the rightmost point. On the third one, I chose the one right in the middle. And on the fourth one, I didn't choose any of those. I chose one that's like 75% of the way from the left. So it's like not right it's between the middle and the right. You can choose anything just to be clear, in it, you don't have to choose the same thing for each partition. A lot of students might not know that, but technically, according to the rules, you are allowed to do that. You don't really want to do that because it makes your life a little harder when you have to do more thinking, but you can do that. You can choose whatever is convenient for you to choose when you're finding a Riemann sum, if they don't specify how they want you to find it. I'll say that. Cool. So now that that's set up, let's try to actually approximate the area under the curve with what we have here. Think about exactly what we'd have to do. The whole idea is that the whole area is approximately equal to the area of the first rectangle, or the first partition, the area of the second, plus the area of the third, plus the area of the fourth. In this example, we're just using 4 partitions. So that's the first trick. And now the question is, what is each of these? So the area is going to be, think about what A1 is approximately. Hopefully it makes sense that it's literally the first y value. So I'm just going to say y1 star. It's literally whatever the y value is that we're choosing. And again, we could have chosen anything in here as long as it's within the partition. That's what the star means. It's like you can choose any sample height that you want as long as it's actually in that partition. You can't choose something way out here. But that's basically the y value right here, whatever that is, that distance from 0, that's really the height of our rectangle. So you can kind of think about it, I'll just call it height 1 times width 1. So you want the height of the first rectangle, the width of the first rectangle. So that's height 1, width 1, and then height 2, width 2. And in general, they'll change, but you can do that for all of them. So if I write it like this, height 2, width 2. Let me make some more room here, actually. I'll pull this over. Plus height 3, width 3. So we're just literally using the area formula for rectangles. And we just have a lot of rectangles, 4 specifically in this case, but you could have more. This logic works no matter how many you have. So there we go. And as we just said, what is the height, or how can we find the height? It's literally our y sample point. It's literally the y value. It's some sample y value in the first partition. That's what this means. That's what the star means. It can be anything, and it'll still work. And then now, this is another thing that's worth thinking about. What is the width? The width, if you think about it, is really the change in x. So it's literally the change in x from there to there. So we usually call that delta x. So I'm going to call this delta x1. So again, the y value itself is the height of the rectangle. The width is the change in the x from that in that partition, I'll say. So there you go. That is 1, and you can basically do this for everything. So you're just doing this for each rectangle. So y3 delta x3, and finally y star 4 delta x4. So there you go. And I know I'm running off the page a little bit. Let me pull it in. There you go. So that's what we're doing. And then now we have that. At this point, well, you can actually do one other thing that's worth doing here. Because the function that you might be dealing with at each point might be different, one thing that's kind of useful to do is abstract away the y values. So instead of saying the y sample point, what you can do is you can really turn it into f of the x sample point in that spot. So that would be like f of x star 1 times delta x1. And hopefully that makes sense, because if you can basically switch the problem, instead of trying to find the y value, because the function can be different in general, which is why for different problems you'll have different y values, because you have different functions that we're trying to find the area under. So it's actually more convenient to just find the x value, because that doesn't change. Regardless of the function you use, the way you choose the x's doesn't really change. So you can reframe the problem to just choose the x values that go to that y value when you plug them into the function. So, and if you just choose the right x values, you can just literally feed them into the function, and that'll automatically get you out the right y values. So that's one thing we can do here, just as a simplification. And this is what you'll see in the formula whenever you see this. This is why, because it actually is like more generalizable if you do that. If you just focus on finding the x values. So that's good. And then if I write this, and one other thing, I'll just throw this out there. You can see as I'm doing this, I'm kind of writing a lot of stuff here. Over and over, it seems, right? It's really just, I'm writing the same thing over and over, but I'm just changing the indices for the partition. So we'll deal with that in a second. Like I guess the thing I'll point out here is it's kind of annoying, you might notice. And yes, you're right, it is annoying, which is why they introduced something that we'll talk about in a second called basically summation notation, so that you can kind of cleverly not have to do this and write it as a formula instead. But right now I'm just writing it out. So there you go. Now, what I'll say is if each partition has a different width, a different delta x. So like delta x1, for example, the width of the first partition could be different than delta x2, which could be different than all the others. So like each of these partitions, they don't have to have the same width, and you don't have to choose the y values, or the y values the same, or the x sample points to get the y values the same. So if everything's different, this is the best that you can do. This is the best you can do to approximate the area under the curve if you want to use 4 partitions. You could also make it better by using more partitions, like 5, 6, 8, 100. Things will get better the more partitions you use in general. That's something else we'll talk about later. But in terms of the formula itself, this is about the best that you can do. However, if you make certain simplifying assumptions, then you can actually go quite a bit further. And there are a couple reasons why you should make those assumptions. One is they make your life easier because they make the formula easier. So even though you can choose things differently each time, it's not a good idea to do that. You actually want the opposite. There are already enough moving parts of this. It's already complicated enough. You don't want to make it more complicated by doing things differently for each partition. You want to make it consistent, and then it can be a lot simpler to keep all the moving parts in your head. So one simple thing you can do is you can just, again, if you have the choice, some problems you don't have the choice. Some problems you have like, instead they won't actually give you the function, they'll give you like a table of values, and they've given you the values spaced out in a certain way that they're essentially forcing the delta x's to be different, like the width of each partition to be different. In those cases, you're stuck with this. But if they tell you the function and they let you choose, you should always, just to make your life easier, choose delta x to be the same for each. So instead of having a separate delta x for each partition, literally, you can just set them equal. So you can just say at the beginning of the problem, just to make my life easy, I'm going to make the width of each partition the same. And when you do that, you don't need a different variable for each one. You can just call them all one delta x. And when you do that, hopefully it makes sense that you can do something pretty sneaky algebraically. I'll write it like this. You can basically factor out that delta x that is now the same variable out of everything. So you can write it like f of x star I, or sorry, 1 I mean, plus f of x star 2, or x2 star. So you can literally kind of just add up the y sample points, which is what we're doing now. Add them all up. And then at the very end, multiply by delta x. So it's like we're just factoring that delta x on the outside. And that's what we have down here. So there you go. And now we're almost done. We're almost done with our simplification. I'll scroll down a little bit. But here, there's still something else that we can do to make this a little bit easier. And this is what I was talking about before with summation notation. What I'm going to do now is I'm going to replace everything in here with a summation. So here you can see, actually let me do it like this, so just make it clear. You can basically use summation notation, and we'll explain this in a second. This is the Greek letter sigma, and then I'll go from I equals 1 to, in this case, 4. And then I'll just say f of x star I. And then times delta x on the outside. What does this mean, or why do we do it? So basically, sigma is it's based kind of like the capital Greek letter S, or that's one way to think about it, S for sum. So whenever you see this in math, this sigma, it basically means add a bunch of stuff. Now, in this case, so in the way it works is you can see that I is what's called our index, or our iterator, usually index. You can use other variables too, like k, n, whatever. But in this case, I'll just use I. Basically, the way it works is start off with I equals 1, and then plug it into this equation. That's your first term. And you see how if I do that, if I just plug I equals 1 into the equation, I get the first term here. And then the trick is just keep increasing I by 1. So the next one will be 2, and then do it again. That's your second term, f of x star 2. And then keep doing that. Just keep adding every time you do that. That tells you the next term, and you just add up like f of like, or the next iterator would be 3. And you just keep doing that until you get to the top number here. So whenever you see the top number here, that's when you stop. But you still include that one. So if I'm going from 1 to 4, you can see that I don't stop right before 4. I actually include 4 and then I stop. So this is really just a convenient shorthand to represent the same thing that we're dealing with right here. And you can see it's a lot less writing too. Like I don't have to write f x star some new number, f x star. I don't have to do that repeatedly. And again, we're only doing 4 here, and it's getting annoying. Imagine if you had to do 100 of them. If you wanted to represent 100 of them, all you have to do is change this number to 100, and there you go. Now we're conceptually representing if we had 100 partitions without a whole lot much writing, or a whole lot more writing. So that is summation notation. Hopefully that makes sense. Now, what we have now, is the Riemann, or this is an example of a Riemann sum. And remember, the whole point of this is that we were approximating the area with this. So this right here is our approximation of the area. Now the question is, how do you actually use it in practice? So how do you actually calculate each of these things when you're trying to approximate the area under the curve of some function, with Riemann sums? So let's change things up a bit and assume that you want to actually calculate an approximation, remember not perfect, but an approximation for the area under the curve of this function using Riemann sums. How would you actually do it in practice? And let's pretend here, usually they'll give you this information that they want you to find it specifically between x equals a and x equals b, a being 1 here, and then b being 9. So let's assume that. Then, and let's say they want us to use 4 partitions. Again, you can see up at the top here, I've left just n. So we don't have to use 4 partitions. We can use as many as we want unless they tell us to use a certain number. So let's just pretend they told us 4. Think about how you would do that. Think about how you would actually figure out delta x and f of x star for each of these. The first thing that you have to do, or the simplest thing probably, is to find delta x. So how would we do that? And again, we're operating under the assumption that delta x, the width of each partition, is the same for each partition. If it's not, you can't really do what we're about to do. But if you make that assumption, go ahead and pause the video and think about how you would find delta x in this situation if we're trying to use 4 subintervals. In this particular case, the delta x of each partition would equal 2. Now, why is that? Well, here, if you think about it, what's the width of the entire partition? So the width of the entire partition would be 9 minus 1, right? Because we're essentially finding the width of this whole thing. So the width of that is just going to be 8. Hopefully it makes sense. Start at 1, go up to 9. So 9 minus 1 is 8. That's the width of the whole partition. And then how would you find the width of each individual partition? Well, the logic is if you have the width of the entire shape and you're breaking it into 4 equally spaced slices, then divide by 4, basically. Or divide by however many partitions you have, divide by that number. So here, 8 divided by 4, that's how we get to. And you can always use this process in general. Again, as long as all the delta x's are the same, you can always use this formula. Just to generalize it a little bit more, you can think about what we did here. We did b minus a over n. This formula is always what delta x is. It's literally b minus a, which will give you the width of the entire partition, in this case 9 minus 1, and then divided by the total number of partitions you want, in this case 4. So 8 divided by 4 is 2. Now if we actually draw this out, hopefully you can tell, if I actually try to draw partitions here, if I try to draw 4 equally spaced ones, you can kind of see it right here that, yeah, that actually does make sense, right? So looking at these, you can tell that, yeah, between 1 and 3, that's the first partition. Between 3 and 5 is the second. 5 and 7, 7 and 9. So yeah, each partition, the width of it actually is 2 in this example. And you can just blindly, you can always rely on this formula when the delta x's are the same. So there you go. This is a formula worth remembering. So that's fairly easy to find the width of each partition. It's a lot more complicated to find the height of each partition because in general those are different. Now, remember what we talked about before. Technically, you can choose whatever sample point you want as long as it's actually in the partition. And as long as you do that, you'll get a decent approximation. But usually in these problems, they'll specifically tell you how to pick the sample values. Usually, they'll tell you to pick using the left approximation, which means choose an x value that is the left of the interval, so the leftmost x value when the interval, and then whatever the y value is there. That would be like a left approximation. again, assuming we're talking about the first partition. And then that's one option. The other option is the right partition. So choose the rightmost xth sample point that you can, and then pick whatever y value goes with that. Or sometimes it's the midpoint. Pick one dead in the middle, and then see what y value goes with that. Those are some of the options, and typically in problems they'll tell you to use one of those. So let's think through how each of those would work. So here, I'm abstracting the problem away from what we're actually dealing with here, because we really just need to focus on the x values. We don't even need to focus on the y values. If we can pick the x values correctly, we can just plug them into the function, and that'll tell us the right y value. So it's all about picking the x values correctly. Let's start with a left approximation. So if we're trying to do a left approximation, what does that mean? Go ahead and pause the video and see if you can think about how to do this. We're basically trying to find an equation but basically I want an equation that tells me for xi star, I want an equation that tells me based on variables that we already know. And again, think about this visual. This is the most important thing. If each partition has a width of delta x and we're starting at A, think about this visual and see if you can come up with an equation that tells you when you plug in a certain y, it'll tell you how to pick the left sample point within that partition. So go ahead and pause and see if you can figure that out. In situations like this, you really want to try to write out a couple, like write out the first few, for example, and then try to generalize it afterwards. It can be kind of tricky to just jump straight to the generalization, so let's come back to that. Let's just write out a couple to see if we can notice any pattern to begin with. So what would be the first sample point if we're choosing according to the leftmost sample point in each partition? Well, if we're in the first partition, we can choose a lot of values, right? So we have a lot of values to choose from. We can choose any x value within that partition, and we want to choose the leftmost one. Well, in terms of variables that we know, what would that be? That would just be A. Hopefully that makes sense. It's literally just the lower bound here. And then now let's hop over to the second partition. Again, we can choose anything in here, but we want to choose the leftmost value. We can't go outside of the partition like that, but we do want to choose something that's furthest to the left that we can go without leaving the partition. What's that one? Hopefully it makes sense that that one is equal to A plus delta x. And then for the third partition, that would be right there. That would be the left value. Hopefully it makes sense that that one is equal to A plus delta x. So we're starting at 0, going to A plus delta x plus another delta x. So it's really plus 2 delta x's. And hopefully at this point you can kind of see the pattern. The sample point for x3 would be A plus 3 delta x. And we could kind of continue along there. Or sorry, this is 3 right here, my bad. I meant to say that sample point for x4 should be 3 delta x. So what's the pattern here? What's the common thing? Well, the A, that's not changing. You notice that it's always A plus something at the beginning. And then we are multiplying by delta x's kind of every time, not on the first time, but every time after that, we're multiplying by delta x's. But what is changing, the way you can imagine it at least, and this is actually a better way to think about it, look at this first one as 0 times delta x. Look at this second one as 1 times delta x. And you can kind of abstract it so that this is the only number that's changing every time. And then what is that number? Well, that's just, if you notice the pattern, when I is 1, this number is 0. When I is 2, that number is 1. When I is 3, that number is 2. It's literally just I minus 1. So there you go. This is the formula. If you just blindly use this formula after you've calculated delta x and after you know what A is, you can automatically find the leftmost sample point of any partition by just plugging in whatever partition you want for I. So hopefully that makes sense. Now let's do something similar for the rightmost partition. So now let's try to find the right approximation for everything. So here, again, if we're starting off in the first partition, we can choose anything in general, but if we're choosing according to the rule, choose the rightmost sample, you can go there. What is that? Hopefully it's clear that that's x star. So x star 1 using the right rule would be A plus delta x. For number 2, it would be A plus 2 delta x. For 3, it would be A plus 3 delta x. I won't go through everything, but if you kind of are following along here, hopefully it makes sense that, actually, I will pause. Go ahead and I'll pause and see if you can figure out what it should be. So here, Hopefully it makes sense. It's very similar to the last one, but it's with a slight difference. It's just a plus I times delta x. It's actually a little bit simpler than the left one. Remember with the left one, it was like I minus 1 times delta x. Here's just I. So this is the rule for how to choose the right sample point on each one. Now, let's see if we can figure out a rule to find the midpoint rule. So the midpoint rule says that, again, normally we can choose any value we want as the sample point, but the midpoint rule says let's do the one exactly in the middle. So in the first partition, it would be there. In the second partition, it would be there, right in the middle. Third partition, it would be there, right in the middle. Go ahead and pause the video and see if you can come up with a rule for that. Now this one, I won't go through and actually work it out, but I'll just say what it is. X star I, so the X sample point that we're looking for is actually A plus I minus 0.5 times delta X. So there you go. This formula will tell us how to always choose the X sample point for the midpoint. So to summarize the rules for each of them, each of the main options you can do, these are what you can follow. If you just blindly follow these formulas, they will tell you how to choose the right sample point. Now, what's interesting here, I'll just give some more context for how to think about it. One way to think about all these, or the right way, in my opinion, to think about all these is just think about the right, basically A plus I times delta X. This is the simplest one, is when you're choosing on the right. Basically start at A and then however many delta X's you have, whichever partition you're in, that's how many delta X's you have. And then you can pull back by a certain amount. That's kind of how I think about it. So with the left, doesn't it make sense that we're basically doing the same thing as the right, except we're pulling back a whole delta x. We're pulling back one delta x. So you go to the right for the first partition and pull back a whole delta x. That'll get you to the left. For the second partition, go to the right and pull back a whole delta x. That'll give you the left of the partition. And then for the midpoint, it's kind of the same thing. So for the first partition, go to the right and pull back a half delta x. That's why we subtract 1/2. For the second partition, go to the right and then pull back a half. For the third, same thing. And that's how it works in general. Go to the right and pull back a half. So that's kind of the common pattern that these have, and this is how you can think about each of these. Now, to be honest, in reality, I think of these as a little overly complicated. So these formulas are true, and we use these in other situations, specifically the right one. That's the one we use the most when we get into something later called an integral, or a definite integral. But in reality, I think these are overcomplicated. The simplest thing you can do, in my advice, is just use common sense to figure out the first one. That would be my advice. If you can figure out the first sample point for x, and again, this works no matter what method you're using, but just worry about the first partition. Don't worry about these general formulas. Just kind of figure out, what's our starting value. If I'm doing the left, then that's going to be my starting value. This is assuming, by the way, you already know what A and delta X are. If I'm doing the right, well, you do have to use a little bit of common sense to say, okay, if I want to go to the right, I'll actually have to go delta X more than A. And then if I want to go to the midpoint, it's like I start at A and then I go half of a delta X to the right. But whatever you do, just figure out the right spot in the first partition. After you figured it out, so like assume this is the correct spot if you're going to use a left approximation for the first partition. After you figure out the first spot, if you want to get to the next spot, all you do is add delta x, and that'll automatically put you at the left of the next partition. And if you want to get to the next one, just add delta x again. You can just keep adding delta x to get to the right spot in each partition afterwards if you figure out the first one right. And again, this applies to the right and the midpoint. So like if we're doing the midpoint, assuming you get the first one right and you've convinced yourself that it's right with common sense, just add delta x and it'll automatically put you right in the middle of the next one. And then add delta x again, it'll automatically put you right in the middle of the third partition. Add delta x again to get to the next one. So that's my advice. My advice is basically, even though these are true for most use cases, probably ignore them and just use common sense to convince yourself that you figured out the right x value for the first partition. That should be where all your effort goes. And then after that, you can just add delta x to jump to the next ones. And as long as you got the first one right, you're guaranteed to get the others right. Now, be very careful with that. If you get the first one wrong and you jump by delta x, you're actually guaranteed to get all the other ones wrong too. So you have to be certain that you got the first one right before you kind of build the logic off of that to get to the others. But that's what I think is the easiest. I think that's easier than thinking through these formulas, even though these are true. As you're working through Riemann approximations, trying to approximate the area under the curve, one other thing that I would recommend is to use this Desmos animation that I'll show here. You can grab the link to this under the video in the description. But basically, what this allows you to do is plug in your function, right? So sine of x, you can also change it. So like if I change it to x squared, it'll auto adjust, but you can plug in sine of x. I'll just plug in that here. So you can plug in your function. You can plug in your lower bound. That's basically this point. And you can also adjust that. So you can also adjust that left and, or you can also adjust that to whatever you want. You can plug in your upper bound. That's the other one. And then you can plug in the number of partitions you want. Here, I'll just stick with 4. And usually you'll be given all of that by the problem. One other thing that they'll usually give you in the problem is which method to use. So you can, right now, hopefully you can tell by looking at it, we're using the midpoint rule. We're grabbing for our y sample points, we're grabbing the midpoint of each partition. By tweaking this, you can use the left. That would be like the left sample point of each of these, of each partition. And if you set this over to here, you're using the right sample point. So this is pretty helpful. Basically, you can plug in what the problem tells you, and it will, one, draw a visualization, which can really help you visualize what you're even doing here. And also, it'll calculate the answer for you. So here, as I change these, you can see that depending on whether I want to use left, midpoint, or right, the actual number changes because I'm using different rectangles. So that kind of makes sense. So it'll actually do all this stuff for you. And this is really useful, I think, for checking your homework problems. You still need to be able to do the technique by hand, like on a test. So like you definitely need to build that skill because it is tricky. But also this is very useful to kind of basically help check your work and see where things are going wrong. So hopefully that's helpful. One other thing I want to leave you with before we go, well, actually 2 things. One is the idea of a negative area. So you can see here, you see how this rectangle is red, whereas these ones are green? That's because this height is negative. So when we're talking about the area under the curve, we can also have negative areas, which is something that we obviously can't have in geometry, but that's new. So here, this red area can kind of cancel out with some of this green area. So that's something to be on the lookout for. That's kind of a common mistake in the calculations, is that you have to pay attention to the sign of the y value. If the sign of the y value is negative, that means that rectangle is going to be negative, and that's actually going to counteract the positive area and make your actual number lower. So that's one thing to watch out for as you're doing these. Another thing is something I mentioned before. Remember what we mentioned at the very beginning when we came up with the idea? Well, we didn't come up with it. Bernard Riemann did, but when we explained the idea of basically using rectangles to approximate the area under the curve. Remember I said that one, the fact that there was a distance here didn't matter. It seems like a bold claim because, like, for example, when I'm using 4 partitions right here, that is not the area under the curve. Like, it's definitely off by a little bit, right? So here, like, this is off, like there are definitely gaps here. And if I use the left, it's probably even more off. So yeah, I'm arguably missing an entire chunk here, even though I'm counting up. So you can, I'll just say you can, well, there's a couple of factors why this isn't that bad actually. One is that you can actually rely on, and again, this doesn't always happen, but just statistically, sometimes when you overshoot or undershoot, they'll cancel each other out. So like right here, I would argue I'm undershooting by a lot. But here, I would argue that I'm overshooting by about the amount that I undershot by here. So a lot of the times, like errors kind of cancel out, which is useful. But that's not the real issue. The real thing that helps is when we basically have, and I'll just say, remember I mentioned before, there's actually a clever technique we could do to make it so that the error is always going to exist, but we can make it so that it becomes less and less relevant, almost not relevant at all, almost. The way we do that is basically by cranking up the number of partitions. So here, this is with 4 partitions, and you can see this doesn't really visually look like the area under the curve. What happens if I keep increasing the number of partitions? What if I go to 5 or 6 or 7 or 8 and just keep cranking them up? So here, if I go to like 12, for example, if I triple the number of partitions, now, again, we're doing the same technique, by the way. This is literally the same thing we were doing, but hopefully it's clear now. It actually looks a lot better. Like here, we're definitely overshooting the negatives, undershooting some positives, overshooting some positives. But in general, like the errors definitely seems to be decreasing. And also you can pay attention to this number as well. Like pay attention to this number. It should change by less and less the higher we get. So as I go from like 12 to, let's say, 30, 50, as I get up here, I can go higher and higher and higher. Now I'm up to basically 100. And we can kind of see what's going on here. Once I go up to, and again, n equals 100, you could go way higher. You could technically keep going forever, and that's something we'll talk about later, how to represent that. But yeah, you can see on this idea that, again, we're still overshooting and undershooting, but by a lot less. So actually, yeah, as you just crank up the n, it actually doesn't matter whether you, right now we're using left approximations, but you could have also used midpoint approximations, or you could use right approximations. It doesn't really matter. Like it's that they're, again, just be clear, they'll always give different numbers if you have a finite n, but the amount that they'll be off by is so close. It's like it's literally hovering between 1.51, 1.53, 1.54. They're so close that it doesn't really matter in the grand scheme of things. You can get a very, very accurate approximation if you use a ton of n values. Now, again, you can probably think about if you had to actually calculate this by hand, it would be a nightmare, and that's true. But the good news is that we've already figured out an algorithm that works, basically. That's what we've done this whole video, is work through the logic of, yeah, this formula should work, and this Desmos animation is already programmed with that formula. So this is something that's good for a computer. Do something simple repeatedly and just do it really quick. That's an ideal thing for a computer, and we can program a computer to do that. That's why this animation is working. So there you go. That's basically what Riemann sums are. We're trying to approximate the area under the curve by using rectangles, by splitting things up into partitions and figuring out the area of each of those rectangles. And now at this point, we've kind of come up with a system to do that, like systematically and reliably. So hopefully that makes sense. Be sure to use this animation like to check your homework problems whenever you have problems like this, where they, where they'll say find the area of the curve between these two bounds with the left, right, and middle approximations using n subintervals. Whenever you get those types of problems, you can definitely use this calculator to verify your work. But hopefully that makes sense. Be sure to grab that animation, and I will catch you next time. See ya.